internet, especially the technical report written by Professor Jack Dongara. Jack's report has already covered a lot of the technical details about this system. So in my talk today, I will try my best to provide some more information about both the system and also the key applications that we are currently developing and running on this Sunway TaihuLight. So this is the outline of my talk today. I will first give a brief overview of this system, and then I will cover the major hardware and software components of this system. And in the last part, I'd like to go through some of the key applications that we currently run on this system. Okay, so Sunway TaihuLight. Actually, yesterday I received a lot of questions about the name. Actually, what do we mean by Taihu? So I put the Chinese name of this system here. In Chinese, it's Taihu Zhiguang. So the first two characters, Taihu, the first one actually means very large in Chinese. And the second one means the lake. So from the name you can see the very large lake, kind of similar to the Lake Taihu in California. And here is a map. So it's actually a pretty large lake in the eastern part of China and very close to the city of Shanghai. And if we sort of zoom in into this area around the Taihu Lake, you can see, even from the map, you can see a very high density of residence areas and also different kinds of highways. So this is traditionally one of the most developed areas in China. And you can, I've pointed out a number of major cities here. So the city of Shanghai is very close. And around the lake you see the city of Changzhou, Wuxi, Suzhou, and a bunch of other cities. Now if you guys do business with China, you probably know these cities. We have a list, not top 500, but a list of cities in China, ranking by their GDPs. So these cities are the frequent top 10 rankers on the list. So you can see this is really a very developed area with a lot of industries. So actually part of the reason that we have this very large supercomputer in this area is that we want to support the upgrading of the manufacturing industries in this area. So instead of just made in China, we want it to be designed in China, innovation in China as well. So, so here is the exact location of our center. It's in this very nice building just by the side of the lake. To give you some more concrete ideas, I put up these nice views of the lake. Especially, you see the lake is especially beautiful when you have light, right? So I guess that's part of the reason that why we call it TaihuLight. And now TaihuLight is not the first Sunway supercomputer. We have the Sunway TaihuLight in the year of 2012. It's located in Jinan with a peak performance of 1 petaflops. Now that system is using the multi-core CPUs with 16 cores in one chip. So compared with TaihuLight, the TaihuLight located in Wuxi has a peak performance of 125 petaflops. So that's roughly 2 orders of magnitude improvement in 4 years' time, which is a pretty big jump in both the performance and the efficiency. And we also see a major change in the architecture. So instead of using multi-core CPUs, for this one we are using a many-core processor with 260 cores in one chip. So unfortunately we don't have any people from vendors to join this meeting this year. Again, I'd like to acknowledge the great efforts by the National Research Center of Parallel Computer Engineering and Technology, who has put together this system, and also Shanghai High Performance IC Design Center, who have put together this many-core processor. So this center is located in Wuxi, and slightly different from previous centers. This one would be run by a joint team. So we have people from Tsinghua University, we have people from the city of Wuxi and also from Jiangsu province. So they will be running this supercomputer together. So just an overview of the specs of the system. So the peak performance is 125 petaflops with a sustained link pack of 19.3 petaflops. The total memory size is around 1.3 petabytes with a total memory bandwidth of 5,591 terabytes per second. So the entire system consists of 40,000 nodes, and if you count the number of cores, is over 10 million cores within this one single system. Now for each node in the system, it comes with one of these many-core CPU, 260 cores, and the peak performance is 3 teraflops for one CPU. And each of them comes with 32 gigabytes of memory and a bandwidth of 136 gigabytes per second. Okay, so that's a quick overview of the system. Now I'm going to kind of go through the major hardware and software components in this system. So this is actually a picture that shows the general structure of the main computing system in the main computer room. We are calling it a 0-1-0 structure. So you can see that these two zeros, these two circles, are actually the computing cabinets that make up the computing system. And this one in the middle is the interconnect cabinets that form our network system. The next slide, we see a more complete picture about the general architecture of the entire system. So the major sub-component system of Sunway TaihuLight include the computing system, the network system, and the periphery system, which includes both the storage and also the management system. The maintenance and diagnostic system, the power system, the cooling system, and also, of course, the software system that support the development of parallel applications on this large supercomputer. So, of course, one of the key innovations that we have in this Sunway TaihuLight supercomputer is this new SW26010 many-core processor. So this is China's first homegrown many-core processor designed by Shanghai High Performance IC Design Center. If we go inside this chip, so this figure shows sort of the general architecture of this and also management services. So this is the periphery system. As I've mentioned, so one part is the storage. We have a total size of 20 petabytes of network storage, which provides a high-speed and reliable data storage services for the computing nodes. The other part is the management system, which includes the system console, the management server, and also the management network. Now, for such a large-scale system, the maintenance and the diagnosis is also an important part. So in the Sunway TaihuLight, we actually have some customized management boards that are integrated into the supernodes, which provides functions such as online maintenance management, status and environment monitoring, fault location and reporting, and also some security services. This slide shows the power system of Sunway TaihuLight. So we have a mutual backup power input of 2 by 35 kilowatts. But when the power goes inside the system, it is converted into DC mode. So for the front end, it's converted into DC 300 watts. And then when it goes to the cabinet, it's converted into 12 volts. For the CPU, it's converted into 0.9 watts. So by using the DC mode directly for the supercomputer, we achieve a much better power efficiency for the system. This figure shows the structure of the cooling system, from the cooling tower all the way to the computing nodes. So for the cooling system of TaihuLight, we actually support recycling of the cooling water, which can actually reduce the utility cost quite a bit. And the heat exchange of the cooling system happens at the level of the computing boards. Okay, so this is for the software system. This one shows sort of the software stack for Sunway TaihuLight, which supports the development of different applications. On top of the hardware system, we have the parallel operating system environment, and we have the storage service. So this Sunway GFS is the major file system, major network file system for the computing nodes. And then we have this RW file system. It's a lightweight file system, which is actually a front-end service for the computing nodes. For the compilers, we support C, C++, and also Fortran, and we provide all these basic software libraries, and we also support these auto vectorization features. For the parallel programming parts, we support OpenACC, OpenMP, and also MPI, which should be supporting the standard of MPI 3.0. And for most of the applications that we put onto the system, we use a hybrid mode that combines MPI and OpenACC. So for different CGs, normally we allocate 1 MPI process for each CG. But for these 65 cores within the CG, we use OpenACC to initialize parallel threads. Okay, so that's for the system. In the last part, I'd like to talk about the key applications we are currently running on this new system. So in our center, we have decided on the following 4 sort of key application domains. The first one is the Earth system modeling and weather forecasting. The second one is the advanced manufacturing. As I mentioned earlier, we were trying to provide support for the upgrading of industries in the Jiangsu province. The third domain is life science, and the fourth one is the big data analytics. So in the talk today, I'm going to mainly focus on the projects that we were collaborating with the Tsinghua University groups, and also we would talk a little bit about these Golden Bear applications that we have been doing in the last year also. So first, for the Earth system modeling and weather forecasting, the first project I'd like to introduce here is our efforts on refactoring and also optimizing the community atmospheric model, CAM, which is probably one of the most widely used atmospheric models in the world. So this one is a collaboration project by Tsinghua University and Beijing Normal University. Now we decided to do this project because we see this is a very typical challenge that we would face when we try to move some of the traditional HPC applications onto the new many-core architectures. So for these traditional HPC applications, usually there's a lot of complexity in the application, and usually we have a heavy legacy in the code base. Like for the climate models, they are usually in the range of millions of lines of code. So obviously we can't do all of these jobs manually, and we need some automated tools to help this process. For the second part, these legacy code, they were designed and written in the last few decades, and they were usually targeted for the multi-core architectures, which makes them generally not suitable for the new many-core architectures. So in our experience, a lot of the tools that we are trying to develop was trying to sort of find the right level of parallelism that you can fit into the many cores, and also the right level of code size and memory footprint that you can fit into these many core architectures. And the third challenge, and also we see as the major obstacle for porting these applications, is that we don't find enough talents to do this. I mean, we have computer engineers, but they don't know climate models. And for the climate scientists, even for them, they don't understand all the different lines of code in the millions lines of code of the entire model. So we see that it's very difficult to find suitable people with interdisciplinary knowledge and experience to do this kind of porting efforts. So now for this porting of CAM, the entire code base of CAM is around 500 million lines of code. So to deal with this CAM program and try to put it onto the Sunway TaihuLight system, we were divided into two parts mainly. So the first part is the CAM-SE dynamic core, which has been rewritten actually, I think in the last decade. So this code is relatively small, and it comes with a very regular code patterns. So for this part, we are doing this porting and optimization by manual OpenACC parallelizations on both the code and also the data structures. Now, the more difficult part is the CAM physics skins. So we have a quite large number of physics skins in this model, and they were written by different scientists in the different times. So most of the code, they come with an irregular pattern, and the code pattern is also quite complex, which means you basically cannot manually accomplish this job. So for this one, we are mainly relying on some loop transformation tools to sort of expose the right level of parallelism and code size for the 260 cores within this new Sunway many-core processor. And we have also developed a memory footprint analysis and reduction tool, trying to fit the most frequently accessed variables into the fast buffer I've mentioned earlier for each different core elements. So here we just show some preliminary results that we have achieved. So this one is comparing the performance when we use both the MPE and the 64 CPEs against the case that we only use the MPE. Now, for both the dynamic core and the physics skins, we see that for some of the kernels, which are quite compute intensive, we can achieve a speed up of around of about 10 or even to 22 times. But for the other kernels, which might involve a lot of memory operations, the speed up is not very high. It's around 2 to 3 times. So this is sort of the speed up for the entire CAM model. Now the scalability is still very good. We can scale up to 24,000 CGs, so that is roughly around 1.5 million cores for this CAM model. But the speed up is not that significant. So by using both the MPE and CPEs, we only achieve roughly 2 times speed up when compared against the case that we use the MPE only. But we see this as a good starting point for us to continue working on the tools and our porting approaches to achieve a good utilization of this new system. So these are some results that we have achieved by using this porting model on the Sunway TaihuLight. The second project that I'd like to talk about here is a high-resolution experimental atmospheric model for Sunway TaihuLight. So this is actually, as I mentioned, an experimental project. Different from the previous one, where we are trying to port an existing model and we are trying to minimize the modifications to the code. In this one, we are more like taking a hardware-software co-design approach. So we have applied some structure change of the model components, and we are trying to do this many-core accelerations of 4 compute-intensive parts. And on top of that, we are applying a loosely coupling scheme. So in normal climate models, the dynamic core and the physics schemes are usually using a tightly coupling scheme. And in our approach, we're trying to use the loosely coupling scheme so that the scale that the number of cores that we use for the dynamic core and the physics schemes can be independent of each other, so that we can achieve a better scalability and a better utilization of the entire machine. And this one is targeting at high-resolution simulation scenarios. So currently we have run experiments for 10 kilometers to 3 kilometers global resolution. And for certain cases, we can scale to the entire system of TaihuLight. So here are just some preliminary results that we have achieved. This is for 10 kilometers resolution. And this is the precipitation for the 3 kilometer experiments. And this one is the surface pressure. Okay, so that's for the Earth system modeling. Another domain that I want to mention here is about the big data analytics. As we can see from this ISC, so this big data thing is actually becoming more and more important application for HPC platforms. So on the Sunway TaihuLight system, we have also started this project to develop an open source deep neural network library. So 2 key goals of this project. One is to achieve architectural optimizations so that we can get both high performance and high efficiency for doing deep neural network, both training and inference on this Sunway many-core architecture. And based on this hardware architecture, we can actually provide a good support for both double precision, single precision, and also fixed point number representations. The second part is, of course, about algorithmic optimization. So the current, most of the current CNN libraries, they usually cannot run, or say they cannot benefit much from running in a very large scale. So we will be working on this algorithm side to try to see what are the basic methods that we can actually benefit from a large scale computing resource and to achieve a better training result. So these are some preliminary performance results for running the convolutionary layers for double precision. So the efficiency for now is not yet very good. It's around 30%, but we are still working on this library and try to make it similar performance to the GPU platforms. Okay, so now I would talk briefly about these Golden Bear submissions that we have made based on our Sunway TaihuLight system. So you can see that we have around 5 key applications that have managed to that have managed to scale to almost the full system of TaihuLight. So some of them are, actually two of them are related to climate modeling. So one is for atmospheric simulation, another one is for the surface wave simulation. And the other ones are for atom level or phase field simulations and for MV simulations. So the first one I want to talk about here is actually a fully implicit dynamic solver for doing cloud resolving atmospheric simulations. So this is a collaboration project by the Institute of Software in the Chinese Academy of Sciences, Tsinghua University, and also Beijing Normal University. So the key goal of this project is to achieve an efficient and scalable solver, which has the following major components: a hybrid microgrid domain decomposition preconditioner, and a physics-based multi-block IRU. And for the solver, we have performed parallelization and optimization at different levels. So I'm not going to explain all the details in the figures, but basically we are performing a very careful optimizations of all these different components related to the solver. So for different parts, we are taking a different parallelization approach to make a full utilization of all these different cores in the system. So this is the results of this solver. So when this work was submitted, we actually we actually don't have the full system yet. So at that time we have a number of 32 cabinets in the system, which is roughly 8 million cores. So you can see that the solver can actually scale to the full scale of 8 million cores, and the efficiency is capped at around 50%. The performance is above 2 petaflops, which is pretty good for an implicit solver. The second one I want to mention here is this global surface wave simulation, and is a collaboration project by the First Institute of Oceanography and Tsinghua University. So again, you can see that one of the major approach we need to do here is that we need to consider about the algorithm and try to achieve a balanced and synchronized utilization of both the MP and all the 64 CPEs. And this is the performance result that we have got for this surface wave simulation. So again, we can scale to up to around 8.5 million cores and achieve peak performance for 30 petaflops. Now, of course, this one is using an explicit approach. The third one I want to mention here is this atom level simulation of silicon nanowires. This project is done by the Institute of Process Engineering, the Chinese Academy of Sciences. So again, this one also manages to scale to the level of 8 million cores, and the performance is around 6 to 14 petaflops in double precision. The last project I want to mention here is this phase field simulation, which is done by the Computer Network Information Center, Chinese Academy of Sciences. This one is also taking an explicit method, but this method has this advantage of maintaining a pretty large time steps. So in certain cases, the time step of this approach can be actually longer than some implicit methods, and it can achieve a peak performance of around 40 petaflops. And as mentioned yesterday, we were quite excited to know that 3 of these 5 submissions actually were selected as the Golden Bear finalists. Okay, so that's pretty much all that I want to share at this talk. And if you want to find some more details, you can come to our booth at 4:30, and we have a nice model of this new Sunway TaihuLight system. And there's also a recent paper about this TaihuLight system and its applications. Thank you.